We've seen before that the graph of a function is concave up when f prime of x increases. F prime of x increases means the slopes of the tangent lines increase. Well, let's think back about what it meant to be an increasing function. If a function was increasing, going up, that means its slope was positive. So if f prime of x increasing, that would mean the slopes on f prime of x are positive. The slopes on f prime are positive. That would mean its derivative is positive. F prime of x prime is positive. Slopes, derivative. Okay. Well, we can write this as f double prime of x, positive, so that the graph of a function is concave up when f double prime of x is greater than 0. So let's put that up here. F double prime of x greater than 0. And then similarly, we can say that the graph of a function is concave down if f double prime of x is less than 0. So now we want to look at f double prime of x and concavity, the second derivative and concavity. Let's look at a function, a graph of a second derivative. So this is the x-axis, and this is the second derivative graph. We want to know about the original function. Find the concavity for f, the original function. The graph is concave up if the second derivative is positive. The positive numbers here are above the x-axis. So the numbers here, above the axis, those would be positive numbers. So that means that on both sides, here and here, we have it positive, above the x-axis, concave up for the function. Down here, both this piece and between here, we have below the x-axis. So we have negative values for the second derivative. Now let's see. Let's put some numbers on here. Let's make this negative 1.2. That's certainly 0, and this is probably supposed to be about the same, positive 1.2. So that if you want to think of it on a number line, you can do that also. We can say that, let's look at negative 1.2, 0, 1.2. To the left of negative 1.2, below the x-axis, negative numbers for the second derivative, f double prime negative. So the original function is concave down. Between negative 1.2 and 0, all of those numbers are positive. The second derivative is positive, so the original function is concave up. Notice that for the second derivative, I'm looking at positive and negative values. And what I chose to look at to divide them up are the places where the derivative is equal to 0. So my big dots, f double prime of x is equal to 0. From 0 to 1.2, it's below the axis, that's concave down again, and then finally above the axis makes the original function concave up. The derivative, just like it was with the first derivative, we think in terms of positives, negatives, and zeros. For the derivative, we look at numbers. For the function, we look at the names. So the original function is concave down, concave up, concave down, concave up. They don't always alternate like that, we've seen. And the signs are what tell us that for the second derivative. Now, you don't have to draw a number line. You can just think about above the axis and below the axis. Now, if we think in terms of intervals, we could write this in a different way. We can say that if I look at intervals, I have concave up. I could say from negative infinity, not negative infinity, negative 1.2 to 0, and from 1.2 to positive infinity. Those are the intervals. You can write them in terms of just x's. Negative 1.2 less than x less than 0. For concave down, that's where we get into negative infinity up to negative 1.2, and then from 0 to 1.2. And I'm not including endpoints. These are not points. These are intervals, because at those points, we have the places where it is possible points of inflection. So when we have possible points of inflection and we see that they've changed, these are our definite points of inflection because concavity changed there. So the red are points of inflection because concavity changed. We saw graphs where possible changes in concavity occurred where the second derivative was equal to 0. Right on the number line, on the x-axis, the derivative graph crossed, the second derivative graph crossed, so it was equal to 0. But it's also possible that concavity can change when the second derivative at a point does not exist. But we haven't really looked at any of those. So let's look at a second derivative graph. And the problem is that there's an asymptote here. Say this is negative 2. And the graph of the second derivative looks like that. So we have a vertical asymptote for the second derivative. So what we have here is that there is no point, no value for f double prime of negative 2. You can't plug the number in because there's an asymptote there. So that means that the possible inflection point does not exist. So there's no value for that, so there's no inflection point. However, note the concavity. On this side of the graph, it's concave down. On this side of the graph, it's concave up. So concavity for the original function did change, but there is not a point of inflection. You can't have a point of inflection if you don't have an xy value for the point. So changes in concavity can occur either where the second derivative at a point is 0 or where the second derivative at the point does not exist. And this is an example of looking at the second derivative graph. Well, let's look at a function f and see how we can decide whether or not there's going to be an inflection point from the beginning. Suppose our graph looks like this. Right in the middle here, what we have is a very vertical piece, very straight up and down. Vertical lines. What's the slope of a vertical line? The slope of a vertical line has no slope. Vertical line has no slope. That doesn't mean it has 0 slope. When it has 0 slope, it's horizontal. When it has no slope, the slope does not exist. And so any original function that has a vertical tangent line at a point, the concavity certainly can change there, This is concave up on this side. It cups up. Concave down on this side. So concavity can change, but when you get to the second derivative of the function, there is no second derivative at that point, and there is no point of inflection. But the concavity does change at that point. We don't see these a lot, but we see them sometimes. This is very similar to a logistic graph, but not exactly. So there is a possibility that you will at some point find sometime when the second derivative does not exist, but concavity does change. Now we're going to see how we can use the second derivative formula for a function to determine the concavity and inflection points on the graph of the function. We found out that the concavity changes when f double prime of x is equal to 0 or f double prime of x does not exist. We also know that the function is concave up if f double prime of x is positive, and concave down when f double prime of x is negative. So that's what we use when we have a formula as well as when we have a graph. Let's look at the function f of x equal to x to the 4th over 4 plus 4x cubed over 3. And we want to find out where it's concave up and down, but first we want to know where our possible changes occur. So we need to take the second derivative and set it equal to 0. Well, to get to a second derivative, you have to do the first derivative. So f prime of x, we keep the 4 constant in the denominator, take the derivative of the numerator, 4x to the 3rd, plus, for the second part, keep the 3 in the denominator. The derivative of the numerator, 3 fourths, are 12x to the 3rd. Excuse me, 12x to the 2nd. So I can simplify that. X cubed plus 4x squared. And then I need to take the second derivative. Derivative of x to the 3rd is 3x squared plus the derivative of 4x squared is 8x. So that's my second derivative, and that's what I have to use to find out the concavity. We've talked earlier about using the first derivative for concavity, but this is the most direct route if you don't need the first derivative for anything else. So I have my second derivative, and I want to first see where it's equal to 0, and I need to factor. I can pull out an x. What's left here is 3x plus 8. So when I set this equal to 0, I either have x equal to 0, or I have 3x plus 8 equal to 0. Then x would be negative 8 over 3. So I have 2 points where concavity may change. So like when we were working with first derivative for a formula, with the second derivative, we're going to also put these on the number line. So let's put 0 and negative 8/3. And again, I'm not putting anything else because all I'm interested in are these 3 different intervals, these regions of the graph. So I use test points. I need a test point in this interval, and I want to plug it into the second derivative and see what I get. Well, negative 8/3, if I had negative 9/3, it would be negative 3. So let's put in negative 4 just to be sure I'm pretty far away down in this interval. If I plug this into my second derivative, if I plug negative 4 in here, I have a negative. 3 times negative 4 is negative 12, plus 8 is still a negative. So when they multiply, we have a positive. So f double prime is positive on that interval. We move between negative 8/3 and 0. Well, let's use negative 1. Put -1 in for x, it's negative. -1 in here would be -3 plus 8 is positive. Multiply those two together, I have a negative for my second derivative. I have one more interval to check. F double prime at, let's say, +1. X equal to 1 is positive. X equal to 1 here is positive. Plus 8 is still positive. So this part of the graph will also be a positive second derivative, and from there I just label what the concavity is. So my function f, since the second derivative is positive, concave up here, concave down here because it's negative, and then concave up again. If you want to write those in intervals or with x's, I would say it's concave up for x less than -8/3, concave down for -8/3 less than x less than 0, and then concave up again for x greater than 0. So you can use interval notation or you can use x's, whatever the problem you're working on needs. We want to look now at the formula for a second derivative already given to us. It's complicated enough that we don't have to start with a function and take a derivative. For concavity, we use second derivative, and we already have it here. So let's think now, what do we do next? Well, concavity changes when the second derivative equals 0. So that's what we'll do first. We'll take our second derivative and set it equal to 0. After we do that, we know that when the second derivative is positive, the function f is concave up. When the second derivative is negative, the function f is concave down. So we come over here and we look at the pieces when this is equal to 0. X plus 1 could equal 0, in which case x equals -1. X minus 1 squared could equal 0. And don't let that scare you. If you have a power, you just take that root, the square root of both sides. Square root of this piece gives me x minus 1. Square root of 0 is 0. So I have x equal to 1 from that piece. So I have two possibilities, and I'll do like we did with first derivative, put them on a number line and test in between. My changes could happen at 1 and at -1. And then I'll test in between those points to see where I have concave up or down. So let's pick a point here, say -2. F double prime at -2. If I plug -2 into the derivative, -2 plus 1 is a negative. -2 minus 1 is -3, but I'm squaring it, makes it positive. A negative times a positive equals a negative. So I have a negative on this interval. Let's pick a test point here. I like 0, between -1 and 1. 0 plus 1 is a positive. 0 minus 1 is a negative, but when you square it, it becomes positive. So this piece is positive. One last interval to check, f double prime, let's say at +2. 2 plus 1 is positive. 2 minus 1 is positive, but squared makes that piece positive. So this piece is also positive. So when we look at our derivatives here, I have it a negative, then a positive, then a positive. So the original function f would be concave down. And then on this interval, concave up. And then over here, it's concave up again. So it did not change. Okay, there's no change there. So when I talk about where my function's concave up and concave down, I would say the function is concave up from -1 to 1, and then again from 1 to infinity. Something happens at 1. So I'm not including it as concave up or down because it was the place where I thought it might change, but it did not. It's concave down on the interval from -infinity up to -1. And what about inflection points? Well, it certainly changed here. So we do have an inflection point at x equal to -1. No inflection point at x equal to 1 because concavity does not change. There's no change, so that is not an inflection point. We're in a section talking about the second derivative formula, and now we're going to talk about it, relating it to extrema. Now, before we learned that possible extrema occur when the first derivative is 0, or when the first derivative does not exist, and only the first derivative. So how is it going to work with a second derivative? Well, let's think about a very basic little graph. I always like to think about a parabola. If we were looking for the extrema for this parabola, and we took the first derivative, set it equal to 0, that would be a horizontal tangent line. It would be right here. That would be where f prime was equal to 0. Notice the concavity. This is concave down. So if a function is concave down on an interval and there's a place where the first derivative is 0, this would give us a maximum, a relative maximum. Let's think about the other type of parabola. Opens up. If the first derivative is equal to 0, it would be this point down here. This is concave up. This point is where f prime equals 0, and it is a relative minimum. So we can use the second derivative with concavity in order to determine where a function has relative max or min. So let's see how we can do that with a formula. Okay? Let's look at the formula. F of x equals x times the natural log of x. And we want to find where the derivative is 0 because those are the only places where we have possible relative extrema. And then we want to see what that will do about our concavity. So we need f prime of x. This is x ln x, except it really means x times the natural log of x. So we have to use the product rule to get the derivative. Remember, product rule, if it's f times g, would be fg prime plus gf prime. First times derivative of the second plus second times derivative of the first. So we've got the derivative equals the first, x, times the derivative of the second. The derivative of natural log of x is 1 over x, plus the second, natural log of x, times the derivative of the first. Well, the derivative of the first is just 1. Derivative of x is 1. I can simplify this. X times 1 over x is 1 plus natural log of x. Now, the point where I have a relative max or min occurs if this is equal to 0. I have to solve for x. So let's see what that's going to do. Subtract 1. Now we have to push your mind way back to when you were doing your exponential and log things. This natural log is base e. So I can either think of it as this is base e and I rewrite it as e to the -1 equals x. Or you can think about it another way. If this is what I have, we can take and instead of back when you had exponential functions and took the natural log of both sides, you can take both sides as powers of e. So I can, for my next step, make this e raised to the negative 1 power equal to e raised to the ln x power. E to the negative 1 is here. E to the ln x, their inverses, you get x. So either way you want to think about it, x is equal to e to the negative 1, and that is the place where the first derivative is 0. E to the negative 1 is 1 over e. E is about 2.728, ... So I like to say, okay, let's say that x is about a third, something like that, 3/10, 4/10. That is the only place we have when we took the first derivative, set it equal to 0. That's the only place that we would, if we were using the first derivative test, to put on the number line and test on either side of it. However, we don't have to do that. We can go on to the second derivative. Remember that our function now is f prime of x equal to 1 plus ln x. I'm going to go ahead and find the second derivative. Derivative of 1 is 0. Derivative of ln x is 1 over x. What might happen if I plug in 1 over e? Let's see. F double prime of 1 over e would be 1 over e, which is e. So f double prime is about 2.7. That's a positive number. So here I have f double prime of x greater than 0, which tells me that f is concave up. Concave up. The function is concave up. Think back about those little parabolas. The function is concave up. Looks like that. This point down here on that interval is the one where I have 1 over e, and that's the minimum. So at x equal to 1 over e, f has a relative minimum. You can find the actual minimum value if you wanted to go back up here and plug 1 over e in, but we'll just say, okay, this is the second derivative to test the critical number that you get from the first derivative. The numbers that make the first derivative equal to 0 or not exist are also called critical numbers. So you may hear us talk about critical numbers, and that is where the first derivative either equals 0 or does not exist, and those are the only possible places where you can have a relative max or min, and this has a relative min at that point.